unit is called OFDM, but we're only going to get to OFDM at the end. I think this will result in a better experience for you because it means a little bit less jumping into the deep end with some matrix math. So let me preface this with saying we're going to have to use matrices. Well, we don't have to, but I like them, so we're going to. So deal with it. Hashtag. So let's talk a little bit about multiplexing. So the common ones, or the popular ones that you've heard about, are TDM, so time division multiplexing, FDM, frequency division multiplexing, and then kind of the one that doesn't get talked about a whole lot, mostly because it's really hard to visualize, is CDM, code division multiplexing. And we'll talk about that in the next module. The other two are much more easy to visualize. You can see here from the Beard installing textbook that the whole idea is that in one, you chop up one dimension and you use the entirety of the other dimension, and in the other, you flip-flop. So let's talk about TDM, because we just really did talk about FDM a minute ago. But we've got one idea is that you've got many bit streams. So these guys, bit stream 1, bit stream n. And let's say, just for ease of arithmetic down the line, that each of these are delivering bits at a rate of RB over n. And the idea, or one idea, is that we're going to have a commutator that comes along here and picks up a bit every time it hits one of these. And this thing spins around at a rate of RB. Okay, so within 1 second, it makes RB revolutions, and in that time, it spits out RB bits down this pipe. And then this would then get upmixed to the passband and sent on its merry way. So this would be a bandwidth of RB over 2. I guess we can switch to the other color. This signal, because it has a bit rate of RB, is going to have a bandwidth of RB over 2. And then up here in the passband, we multiply by 2 again, and so we get an RB channel bandwidth. This is assuming no pulse shaping shenanigans. Okay, and so the reason, this is one visualization of how TDM would work, and the idea is that each of these streams gets 1 out of n time instances. So another way to visualize this is as kind of a shift register, and that each of these bit streams are given a slot to dump into. And then at the end of the day, these are all fed into some kind of upmixer. So if you think of, there are n slots, so 1, 2, ... up to n, and then we start over, 1, 2, ... that each of the individual bit streams, and you can think of them either as coming from, say, one computer or from multiple applications on one computer, or in the extreme, they can be coming from multiple users, in which case we append an A onto the acronym and call it multiple access rather than multiplexing. But so far we haven't really talked about from whence these bits are coming, because it's really not that important. But you can either think of them as coming all from the same source, but somehow being split up, or maybe a more helpful thought process is you're thinking about a kind of a cell phone base station tower, and there are, I don't know, 200 cell phones connected to this tower. That would mean that if all 200 were active, then in every symbol period, the base station would be sending one person's data to them and then going around. So you'd have to wait 199 symbol times before you got your next update. The benefit, why anyone would want to do this, it sounds super slow and convoluted, is because you get to use the entirety of your channel bandwidth at any given time. But at any given time, you're less likely to get the bits that you actually want to get through the channel if you're sitting on one of these streams. Okay. So the other way, and the other diagram is kind of a rehash of what we just saw, is you have a single bit stream at rate RB. You are going to either buffer or serial to parallel this, and you get actually the exact same picture that we just had. Where each of these you get RB over n times 2, because you're in the channel now. Okay, and the advantage of this, of course, is that you don't have to wait if you're only expecting one of these channels. So again, if you're the cell tower base station and you have 200 people's data that you'd like to get to them, this means that at any given time, each phone is seeing a stream that it can use. Right? There's no holding period. There's no waiting period between symbols. The price, of course, is that you have to divide your total transmit channel into 200 slots, which means that the bandwidth in each slot is small, which means the bit rate in each slot is small. So even though you're getting bits continuously, the rate at which those bits are coming is necessarily impaired because the mini channels, the sub channels, are smaller in width than they would have been in TDM. Okay. Let's see here. I hope you can start to see the problem with this methodology, especially in FDM. And that is the presence of all these dang modulators, right? I mean, sure, you can build a mixer, an RF mixer, for not that much money. But remember that in order for these to be divided, and remember the D is division, in order for these to be divided in the frequency domain, these frequencies that you're modulating with all need to be different. Right? These all need to be spaced apart. We haven't talked about how far they should be spaced apart, but at the very get-go, this should raise some questions in terms of practicality. Is that you would need an oscillator, well, you would need n oscillators, one at each of these frequencies, unless you had some kind of special relationship, like a doubling operation or a halving operation. But again, if we're talking about passband frequencies, like if you're going to double 1 gigahertz, it's not too long before you get out of the range of a practical antenna. Or if you start halving, you're going to get out of the range of a practical implementation anyway. So, and I just mentioned halving and doubling is because those are relatively easy frequency type operations, LO type operations. But in the passband, halving and doubling gets you into trouble real quick because it gets you like into different physics, if you like. So if I want this to be, I don't know, 2.25 gigahertz and 2.225 gigahertz, and so on, just spacing down here by a couple hundred megahertz each, 2.0 gigahertz. Then we start to, like, if you have a lot of these, you start to have problems with just space. Like these local oscillators take up space and their own timing details. And so I just want you to see that FDM, when taken to an extreme, gets impractical. I guess anything taken to an extreme will get impractical. But I want to bring this up because this is the fundamental problem that OFDM will solve eventually. So Perhaps this should have come later in the module when we're ready to talk about OFDM, but I want you to keep this in mind. This is an expense type problem and basically just a circuit problem of just packing this many local oscillators into a transmit. And then whatever you do on the transmitter, you're going to have to do on the receiver to mix them down into the baseband again. Okay, so keep that in mind because OFDM promises to overcome that limitation. I can't really think of a better place to put this into the class, but we should start talking about spectral masks as a guide. So these, I mean, you could enforce them on yourself, but usually it's enforced upon you by regulators that say, look, you have purchased this channel in the passband. That's great. You can do whatever you, not actually whatever you like, but you can do a lot of things in that channel, but we are going to enforce limitations on the power that you leak into neighboring channels. Okay, so this dashed line is called a spectral mask, and you'd have to demonstrate that your radio, that this power spectral density coming out of your radio lives under this mask, right? So a mask is the idea, kind of like in Photoshop, you could apply this mask to the screen of a spectrum analyzer, and anything that crossed it would be in violation, if you like. So yeah, this is kind of a generic formulation. I couldn't find a good one that was nice and simple. But the idea is that if you are transmitting on this channel, then your neighbor would have their own mask and their own channel that neighbors yours. So this is carrier 1, carrier 2. And if you are, so in particular, if these are different entities, then you would need to respect and leak into them as little power as you can. But if these are, say, different carriers on your same FDM system, then at the very least, you're going to have to space them not directly next to each other, because then you'll be interfering with yourself, if you like. Also, pretty darn hard to build a filter that would fit between them, right? The further they're spaced apart, even if you are the only person transmitting in your area, the further apart you space your passband channels, the easier it will be to bandpass filter them on the receive side and get as little inter-channel interference as you can. So the book that I pulled this from is talking about 5G communication, and so this is specifically for gigahertz carriers. So these are things like Wi-Fi, like Bluetooth, like 5G mobile communications, like millimeter waves. Don't expect 40 megahertz between, say, FM radio channels. Like that's. So this all scales depending on what region of the RF spectrum you're in. And then also this stands for base station. And finally, OOB is out of band. All right. Questions on this? So in order to talk about OFDM, one of the reasons that it came about was the idea that people wanted to split their frequency domain into subchannels, but they didn't want to have to do it with actual, thousands of local oscillators. Another reason that OFDM was a big selling point, and I say was because it came about and it ushered in the change from 3G to LTE. That was the big jump in technologies, one of them anyway. And the other selling point was that it helped to overcome channel imperfections. More so than just splitting up the frequency domain, and we'll get into why this is, but in order to get into the why, I need to give this circular argument about what channel imperfections might exist out there. So let's talk about channel models. And I think the first model we should think of is good old LTI. So this is what we have here is kind of an abstraction of everything we've been talking about so far. We have symbols, which are indexed by k here. So time is indexed by k. So the kth symbol is s sub k. And let's, for sake of argument, let's say that these are drawn from QPSK constellation. Okay. And so also the implication is that these are going to be uniformly drawn. So at any given symbol time, any one of the 4 constellation points are equally likely to come through here. Right, so what I've just done is I've said all of a sudden your symbols are now random variables because we're giving them a uniform distribution. More on that later. So one way to model getting symbols from transmit to receive is thinking about each symbol modulating a delta, a Dirac delta. And possibly there could be some time shift here, but I think we don't lose anything by assuming that's 0. And so what we've got here is different complex numbers, sk, modulating deltas that are shifted by integer multiples of the symbol period, so t sub s. All right, so this is then what is sent to the channel. And if we at first model the channel as an LTI system, then its impulse response tells us everything we need to know. And if we are not doing any pulse shaping, then what is essentially happening is that each symbol, right, what happens when I convolve this impulse train with this impulse response? Well, it's kind of like the channel is doing the pulse shaping, right? Because delta star q is q. And if I have some symbol multiplying out here, some constant, then I get that symbol out here. So this is like letting the channel do the pulse shaping. Okay, so we've learned that if we have pulse-shaped transmissions, then in the presence of noise, the best thing we can do is run that received, so this is received, through a matched filter. Matched to what? Matched to the pulse shape. The pulse shape is now the channel impulse response. And then sample. Right, so this is our cross correlation model. So you say, wait a minute, I don't want the channel to do my pulse shaping. Okay, fine. Let's put in another block here. We will have impulse response P of t. And so now we have the same signal coming in here. And so now we've got these pulses. These pulses are then going to be sent through the channel. Get some noise coming in here. And then what should the matched filter be now? What goes here if I am first pulse shaping with P and then transforming with Q?
Would it be P of t?
Well, so certainly we're going to have to do some time reversal. If you're thinking matched filtering, you should be thinking about time reversal. But time reversal of what signal is the question. Think about what is the impulse response of this masked system.
It's P of t convolved with Q of t.
Good. So this is going to be P of t star Q of t. All of that considered a function in negative time. Okay. Right, because at the receiver doesn't care that you've done one shaping here and another shaping there. All the receiver knows is that you've done some shaping, and the way to effectively communicate what's going on here is to just assume that P and Q happened at the same time, and then the total impact they have is their convolution. Okay, so that would be optimal if you knew Q. And this gets to the crux of the matter. Who the hell knows the impulse response of a channel? I mean, you could, what are you going to do? You're going to send some impulses into the air and then wait and see what you hear? I mean, that's actually technically kind of what a pilot signal does. But nevertheless, this Q is, for our purposes, hard to know. Now, you could probably spend a whole 10 weeks talking about that statement and methods to overcome it, things like feedback and measurement and adaptive filtering and all that good stuff. But I think for our purposes, Q of t is going to be hard to know, not least of which because channels are going to be time varying by their nature. If when I say an RF channel, you think the path from your phone to a base station, that changes minute by minute if you're walking down the street. It changes second by second if you're driving in a car. And it changes even faster than that if there are other impediments going on, right? So the fact that we've assumed it being LTI is a big assumption, and we will cross that bridge when we come to it. But I think things are going to be hard enough even if we assume an LTI channel. I think that what we don't want to do is we don't want to assume that we know Q. I think that's the, so don't assume it. Right, you follow what I'm saying? Is we don't know Q of t exists, but let's model the channel as having a Q of t, but we just don't know what it is. I think that's a reasonable compromise in terms of ease of mathematics versus practicality. Okay, so if that's true, if we don't know what Q of t is, then I want to adjust this diagram one more time. So we're going to keep our pulse shape. We're going to keep our channel effects. We're going to keep the noise. But now, my matched filter, I can't know Q. And so the best I can do is match it to what I know. And then in some sense, cross your fingers and hope that that's enough. So that shouldn't be satisfying to you. And that's actually what I'm going to talk about for the next hour or so, is how can we do better than this? This is matched filtering without equalization. And so this module that I called OFDM is actually going to be spent, we're going to spend the first couple hours talking about equalization. This process of equalization is most easily communicated in discrete time. And I want you to want that because of this diagram. If you abstract as much as possible, there are symbols coming in here. We're treating them as symbols times deltas, but they're really just discrete things. And if I draw a box around everything from there to there, at its heart, this is a discrete time system, right? We've got discrete things coming in, we've got discrete things coming out. We're going to have to deal with how the noise gets discretized, but I want you to want this to be a discrete time system. So let's see here. If I write an expression for z of t, well, that'll be the input, which we're going to mount onto deltas. So this is a motivation of how we're going to go from continuous time to discrete time. Those deltas happen every symbol times seconds. And that whole thing is going to be convolved with our pulse shaping system, which is then going to be convolved with the channel impulse response. We're going to add that to the noise process. This is then our received signal in the big parentheses. we're going to pass that through a matched filter where I'm taking this treatment here. And I want you to see that I can use the distributive property of convolution here, that I get essentially two convolutions, this one and this one. Okay, so I'm going to call this noise, how the noise gets filtered by the matched filter, I'm going to call that W of t. Right, I don't know exactly what it's going to look like, but I'm just going to give it the name W of t. And then I'm going to take the matched filter and I'm going to use the associativity property of convolution and say this P star Q star P reversed. So these guys, I'm going to call that H of t. So to be clear here, H of t is P, the original pulse shaping, star Q, the channel effects, star P reversed. That's our matched filter. And this represents what our symbols go through. Yeah, they're added to noise, but this is what we're intentionally doing to the symbols. Which means at the end of the day, that the nth sample of the Z process is going to be the discrete time convolution, H of k, with S sub n minus k, plus W of n, where, strictly speaking, k can run from 0 to infinity. Okay, because I've masked the P, Q, and P into H, this becomes a lot simpler. So this is the Zn that I'm talking about. And so here you start to see, I hope, the implications of having an LTI channel, a memoried LTI channel. Let's talk about that on the next slide. But before I move on, there's a lot of ink here. Any questions? So let's talk quickly about memoryless systems versus memoried systems. Where if you like to replace the word systems with channel and be a real communications engineer, I'm okay with that. A memoryless system was one in which the output could be computed without remembering any past inputs. And in discrete time, that means that your impulse response was, or could be nothing more than the unit sample. 0, 0, something, 0, 0, 0. The robots are angry. Does that make sense why this represents a memoryless system? If I put one impulse in, I'm going to get one impulse out, and no history, no memory is required to compute the output. Whereas in discrete time, a memoried, and I guess I'm assuming causal system, is going to have an impulse response that lasts for multiple samples. Okay, so when you talk about a memoryless channel, that is one in which there's no intersymbol interference. There's no other word for it. But a memoried channel is one whose impulse response lasts for more than one symbol period, if you like it that way. And these actually, the lollipops, let's say that they run from 0 to L. These are called channel taps. Yeah, go for it. Okay, so the longer your impulse response, your channel impulse response is, the more taps it is said to have. And what it also means is that in this convolution that I just wrote, we get to clip it now if your channel has what's called a finite impulse response. We only get to clip it to the number of taps that you possess, h of k times s sub n minus k plus the noise sampled at the nth instant. You see that at time n, z of n holds data from L plus 1 symbols. So at n, z of n has, I don't know, the fingerprints has the effect from s sub n minus 1, s sub n minus 2, all the way up to s sub n minus L. Yeah, that's the price you pay for a memoried channel. And that means that past symbols are going to be corrupting your sampled measurement at each time. Okay, so this is another view on intersymbol interference. Right? If it takes more than one symbol time for the data to get through the channel, then by that very statement, we are going to have intersymbol interference. More on that on Friday. Thanks, everyone.